Hello friends, this is Durga from IT University. Let's wait for people to join and then we'll get started. I hope you guys can hear me and also you can watch my screen. If there are any issues, let us know so that we can actually troubleshoot and fix the issues. Hear me and also you can watch my screen. If there are any issues, let us know so that we can actually troubleshoot and fix the issues. Can someone confirm that you guys can hear me and also watch the screen? So let's give some more time so that people actually join. So bear with us, we'll get started in 2 minutes. So we'll get started in 2 minutes. Meanwhile, if you want to access the material for this session, you can actually click on this link. It's in the chat. It is the second message. Let me actually pin it. I am seeing if I will be able to pin this message. I think all my messages might come at the top. You can see the second message. That is the one which have the link, and it will take you to a page like this, where you can get the reference material for today's session, the link for the video, and also the code, which will be uh, delivering as part of the demo at a later point in time. So make sure to use that link and sign up and access the material. So another 30 seconds or so, we'll get started. So we'll start very soon. Yeah, so if anyone is not able to see the screen clearly, you just have to expand the settings and make sure that you are watching at least at 480p. Because we have enabled ultra low latency for the streaming, if you put 720, it will not be streamed properly. And if you go down below 480, then your screen might be blurred. So make sure you change the quality of the streaming so that you see it clearly. However, even if it is not visible clearly now, at a later point in time, when you come back to this, it should be fine. That being said, let's get started. So the main means the guy who will be giving the demo for today is Sarath. He is a data engineer at GrubHub. He's going to share his experience using Spark structured streaming to achieve continuous applications. I know him for past 5-6 years. I mentored him when he want to join or when he want to search for the jobs after his MS, and eventually he ended up in companies like Thomson Reuters as well as GrubHub now. So he was a Java developer back in India before he pursued his MS, and then he did his MS from Texas. And once MS is done, then he has around 3 to 4 years of experience as a data engineer in companies like Thomson Reuters and GrubHub. So he have rich experience in not only big data. He started with Java development, and then he progressed in his career towards data engineering, cloud, etc. He is very proficient in programming languages like Python, Scala, as well as Java. As of now, he's primarily working on Python-based solutions, both for DevOps as well as data engineering. That being said, now I am handing it over to Sharath. He will introduce himself. If I miss anything, he will give those details to you, and then he will actually get into the today's presentation as well as the demo.
Hi everyone, am I loud and clear? Let me give you a quick introduction about myself. This is Sarath Varma. I work as a senior data engineer in GrubHub. I overall have 7 years of experience in IT. I started as a Java developer, then I transformed my career into the data development. I worked for Thomson Reuters and I worked there for almost 3 years, working on developing the data applications using Hadoop and Spark. And then I learned AWS and I'm a certified AWS developer. Right now I'm working with GrubHub as a data engineer. I work for a platforms team where we provide solutions at an enterprise level. This is the quick introduction about me.
So just give us a moment. Give us a moment. So we will be resolving this issue very soon. It seems there is echo and also audio is not clear. So I'm going on to mute so that he can actually start talking. Please type if you see any issues. So we'll wait for some time to resolve the technical issues and then we'll take it further. Voice is clear now? Okay.
Okay, is it clear now? Yeah, let me start the presentation. Fine. Yeah, I think the audio is clear now. Let me start the presentation. So I have gained knowledge in developing structured streaming applications and continuous applications in the past 6 months. So I want to share my knowledge and I also want to demonstrate a use case, a very simple ETL pipeline use case to demo the continuous applications. So initially, as part of this presentation, I want to walk through some few basics like what is Spark, what are the components of Spark, little introduction about data frames, what is streaming, how you can handle stream data in Spark, what is structured streaming, what are continuous application. People are talking about this buzzword called continuous applications. What is this continuous application? And we'll also do a demo on it. We'll also walk through each line of the code, and then I'll take up the questions on application or on the demo or on the piece of code that we want to demo.
So when it comes to Q&A, there will be two phases of Q&A. First, there will be Q&A between me and Sharath, so that we clarify genuine doubts, because I have a lot of experience in this area and a lot of audience might not have any experience. So there will be Q&A between me and Sharath just to clarify most of the common questions, and then we will take few questions from audience as well over the YouTube live chat.
So what is Spark? Apache Spark is the most actively developed and widely used open source project in big data. It is a general purpose distributed data processing engine. What is a distributed mean here? When there is a requirement to process huge amount of data uh, in a very quick time with high latency, we should perform the same task, or we should parallelize the same task into multiple nodes to get the fast performance. This is the main feature of this is one of the main feature of Spark, and the second important feature of Spark is in-memory computing. So in Hadoop, we have two job phases. One is map and reduce. We have intermediate disk operations that happen between these two phases. When coming to Spark, what they did is uh, once the data first you load the data into RAM, it can be cached on the available memory and reused without being read it again from the disk. So Hadoop stores data from each MapReduce to disk, whereas Apache Spark keeps it in memory, and this will be very helpful when you run iterative algorithms. There will be a very low disk read and write operation. This is also one of the feature of Spark, and Spark is designed to cover wide range of workloads. So you can develop batch processing application. You can run iterative algorithms. You can give it interactive queries. It also has libraries for graph graph and machine learning. It also provides libraries for streaming. So we can say that Spark is a unified platform to do batch processing, run iterative algorithms, interactive queries, machine learning, graph representations, and streaming. Let's walk through the core components of Spark. What is Spark core library? How data frame. What is a data frame? And how the data frame is built on top of Spark core library. What is Spark streaming? What is Spark SQL, machine learning, graphics? I'll give you a very quick overview of all these components. These will be like definitions. I want to just emphasize the definitions, just to refresh your memory. That's it. So this we're not going to go deep into what each component is. I want to give you a very quick update on what this component is, just to refresh, so that it'll be very much easy to go further and understand the streaming. Spark core library is the foundation for parallel and distributed processing of large data sets. Spark core is accountable for all basic IO functionalities, scheduling, and monitoring the jobs on Spark clusters. So task dispatching, network is managed, network and data storage systems and fault recovery. Everything will be managed by Spark core library. And DataFrame or RDDs, previously RDDs, are built on top of Spark core library. So we are mostly using data frames at this point of time, working with the Spark 2.x. So let's understand what this data frame is. A data frame is a distributed collection of data which is organized into named columns. Conceptually, it is equivalent to a relational table with good optimization techniques. A data frame can be constructed from an array of different data sources, like any kind of data files, text files, arrow files. You can build a data frame from an external database or an existing RDD. This is a quick introduction about data frames. And the other libraries are built on top of core library, and they also use this data frame API. Data frame API. This data frame API provides transformations and actions. So SQL and all the other libraries would also use this data frame API. Spark SQL components acts as a library on top of Apache Spark. Spark developers can leverage the power of declarative querying and optimize storage by running SQL-like queries on the Spark data. So if you are familiar with any of the RDBMS, we can perform the same similar queries connecting to the RDBMS database using Spark connectors and run the SQL queries. So this is like a querying engine similar to your SQL or Oracle to work with huge data loads on Spark. Users can perform ETL functions on the data coming from various formats like JSON, Parquet, Hive, then run ADAC queries using the Spark SQL. This is a quick introduction about Spark SQL. And coming to Spark Streaming is a lightweight API that allow developers to perform batch processing and the streaming of data in ease in the same application. So discretized stream is the core concept of Spark streaming. It makes use of continuous stream of input data to process data in real time. Spark streaming leverages the fast scheduling capacity of Apache Spark core library to perform streaming analytics by ingesting data into mini batches. The concept of mini batches is introduced by Spark streaming. So what they do is it is just a batch processing underneath the hood. Everything is batch processing, but the way they create these batches is different in Spark streaming compared to the Spark application. If you're reading a file, right? If you're reading a file and if you're reading a what do you call a stream, underneath operations are the same, but the way they divide this and the way the Spark core library divides this and parallelizes is different. Data in Spark streaming is ingested from various data sources like Kafka, IoT sensors, Kinesis, Apache Flume. Uh, these are some of the data sources. You have many more data sources. Graphics. There are several data parallel tools for graph computations, but they do not tackle with the challenges of graph construction and transformations. Also, the graph computations are inefficient and cumbersome because of complex joins. Graphics is an API built on top of Apache Spark for crossword manipulations and solves a few of the graph-related issues. Spark graphics introduce resilient distributed graph, RDGs. RDGs associate records with the vertices and edges in the graph. So if you have worked with any of the graph database like Neo4j, then this graphics library would be very much similar to Neo4j. All right, so it'll facilitate to do that kind of graph representations with huge data. That's about graphics. Machine learning, MLlib is the machine learning library or the API provided by Spark. MLlib is a low-level machine learning library that can be called from Scala, Python, Java programming languages. MLlib is simple to use, scalable, compatible with various programming languages, and can be easily integrated with other tools. MLlib eases the deployment and development of scalable machine learning pipelines. MLlib library has implementations for various common machine learning algorithms like clustering k-means, classification algorithms like logistic regression, decomposition algorithms like principal component analysis, regressions algorithms like linear regressions. So it has provided few inbuilt libraries or implementation for many of the machine learning algorithms. This is the quick introduction about it. This is the very, very quick introduction about all the core components of Spark. Now let's understand what is Apache Spark. Apache Spark is gaining its attention for advanced analytics because of its in-memory processing engine that is known for its speed as well as sophisticated analytics libraries and support for streaming. So we have discussed about few of the libraries that Spark provides. Streaming library, graphics library, MLlib library. These are all the sophisticated analytics libraries to run on what you call huge data or big data. And one of the reason why everybody is moving towards Spark is its unification. So you'll have a same engine and same API for diverse use cases like streaming, batch processing, interactive querying, ETL, machine learning. So it has combined all of them together, and it provided a unified engine that processes or that handles all these different use cases.
Let me add a point here. So when it comes to Hadoop, if you have to build a ETL process, if you want to run queries, you have to use Hive. If you want to do any advanced programming, you have to use MapReduce. So you have to use a suite of tools to get to solve a problem. Whereas with respect to Spark, everything is under one set of APIs or few modules. And as long as you use a particular programming language like Scala or Python or Java, you should be able to solve most of these problems with one approach. That's why Sharath is emphasizing on Spark as a unified framework.
Yeah, so when coming to Hadoop, right? Hadoop is very much famous for for building batch processing systems. We also have Apache Storm that can handle streaming data. We have Apache Impala or Apache Tej. TEG can perform interactive uh, queries or interactive processing. We have Neo4j, Apache Graphy for graph processing. These are all the different what do you call not the libraries. These are completely different projects from Apache. If you want to work with a real-time ETL pipeline, your system should be capable of handling multiple use cases. So Sparks provides a unified engine uh, to serve many use cases. So let's understand what is a data frame. In simple terms, data frame is same as a table in relational database with column headers. It also shares some common characteristics with RDD, like distributed data frame. Data frames and RDDs are both distributed in nature. Data frame is a distribution collection of data organized into named columns. Uh, Data frames can be constructed from a wide array of sources such as structured data files, tables, Hive tables, external databases, and external RDDs. So data frames are also evaluated lazily. So whenever you perform a transformation or an action, then only the computation happens. Then only the resources would be used. That's a little introduction about this lazy evaluation. Even the RDDs are lazily evaluated. Okay, yeah, so let's also dig a little here why data frames are useful. Data frames are designed for processing large collection of structured or semi-structured data. So observations in Spark data frame are organized under named columns, which helps Apache Sparks to understand the schema of the data frame. This helps Spark optimize execution plan on these queries. Data frame in Apache Spark has the ability to handle petabytes of data. DataFrame has a support for wide range of data formats and sources. It has API support for different languages like Python, R, Scala, and Java. This is, yeah, let's go to the next one. Let's understand what is Spark streaming. Before that, we'll go through what is a data stream. A data stream is an unbounded sequence of data arriving continuously. So your applications would generate logs or events, right? These events will be accumulated one after the other in a specific location, directory, or a database, right? This is a continuous flow of data. So a data stream is an unbounded sequence. It doesn't really have a limit where it ends. It is an unbounded sequence of data arriving continuously. Streaming divides us, right, continuously flow input data into discrete unit for further processing. Spark streaming is an extension of the core Spark API that enables scalability, high throughput, fault tolerance streaming processing in live data. Streaming facilitates low latency data processing instead of doing a batch processing. So streaming, what it does is whenever data gets accumulated, it picks up that data. The drivers would distribute this workload to multiple executors. Multiple executors run this data in parallel, and the results will be flushed out. So using Spark streaming library, you can handle uh, uh, continuous stream of data with very low latency. So yeah, Spark streaming supports data sources such as HDFS directories, Kafka, Twitter. Data streams can be processed with the Spark core API, DataFrame APIs, data machine learning APIs, and can be persisted to file system, back to file system, or databases or dashboards. So yeah, these are the what you call data sources that Spark streaming would support, and the what do you call the output formats that Spark streaming supports. So why Spark streaming applications are difficult? So there are so many moving parts out here, right? So you have data accumulating in a directory. You want to perform ad hoc queries on top of it. You want to store that, manipulate something, do some what do you call do some computations on top of it. I also want to share this data to different locations. You have multiple moving parts when you want to build a real-time production level streaming application. So let's understand what are the challenges that we have in building the real-time production level streaming systems. Streaming applications are inherently difficult to build because of these three what do you call challenges. One is complex data. Data is complex because it's diverse. It comes from different formats. It comes in binary. It comes in text, Parquet, Avro, etc. There are many data formats. They come in all different formats. You have to account the application, the ETL streaming application that you build should be able to handle any sort of data format. Data can be dirty, right? Many data engineers spend most of their time cleansing the data. Every time data is generated, you only want certain data, right? You want to extract some data out of it, remove some data out of it. You want to pick some data and do some computation. So myself as a data engineer, I do data cleansing rigorously on every data set that I process. So data can be dirty. Spark streaming application should be capable of handling this dirty data. Data can be late. You expect the data to be available in certain time, but due to network issue, due to some kind of latency issues, right? Network and computations would delay the data. So your system should be capable of handling this delay of data. So these are all the factors you should be considered. That should be considered when you want to build a what do you call a streaming ETL pipeline. The second challenge is complex workload. Streaming application don't exist in isolation. They exist in collaboration with other components, as I discussed, right? You have to perform ad hoc queries on top of it, store it, extract it, do some massaging on top of this data. All sort of things you have to perform on a single data set. So Spark streaming applications doesn't exist in isolation. They exist in collaboration with other components. So you have to provide a streaming application that can interact flawlessly in fault-tolerant way by combining streaming with interactive queries, machine learning, reporting, etc. So this is also one of the key challenge for building streaming applications. And the third challenge is complex systems. Systems are complex and systems fail. You have to account for that failure. You're reading a Kafka stream, writing to S3 or a HDFS. You're reading from Kinesis stream, performing computations on top of it on an EMR cluster and writing back to S3. All these systems can fail. Your application should have the ability to recover from failure. This is a big tough tough thing to build when you are designing a streaming application. You have to understand where the application failed, and you should have all the recovery mechanism when you build a Spark streaming application. These are the main challenge. There's so many other challenges, but these are the main challenges that you should consider when building a Spark streaming application. Data is complex. You have to handle multiple workloads. You should also handle all the failures when you're building a Spark streaming application. Now let's dig deep little into what is structured streaming. Structured streaming is a scalable and fault-tolerant streaming processing engine built on top of Spark SQL engine. It's not built on Spark. It uses all the Spark core APIs, but it is mainly built on Spark SQL engine. You can express your stream computations the same way you would express batch processing computations on static data. There is no big difference there. All the computations transformations are very much similar. Even so, at this point of time, structured streaming is pretty much immature, right? There are a lot of changes happening. Right now there are few limitations to it. Those limitations are available, are documented in the API itself. So it is an evolving what do you call API or a package. So it is going a lot of changes at this moment. The Spark SQL engine will take care of running it incrementally and continuously and updating the final results as the stream data continues to arrive. Structured streaming provides fast, scalable, fault-tolerant, end-to-end exactly one stream processing without the user having the reason to know about what is the streaming. So you have to understand what this end-to-end exactly one streaming processing. So we'll demo it. We want to demo the same thing and to know how to deliver, how to process a end-to-end exactly one scenario. So this structured streaming is available from Spark 2.3. This is a new latency processing mode. There is also a new latency, low-level latency processing mode called as continuous processing. So we'll also understand what the continuous processing is in the next slides.
So Spark structured streaming is introduced in Spark 2. However, the continuous processing is introduced in Spark 2.3.
Yeah, this is the structured streaming model. The model of structured streaming is very simple. Think about your stream as an unbounded table of data frames. Unbounded table of data frames. You can query this table same as static table in memory. You can apply transformations and high-level API queries. You don't need to worry about underlying architecture of Spark SQL and Spark structured streaming engine would take care of all these things. So you are running your queries on top of an unbounded table of data frames. This is the structured streaming model, how the data is being processed, how your queries get executed on top of that. So continuous applications. This is the new buzzword we are hearing in the big data space. Continuous applications are the end-to-end applications that reacts to data in real time. So when you design a system that reacts to data in real time, we call that applications as continuous applications. You might have so let's understand what is the streaming system and what is this continuous application system. You might have a stream. Right, you don't you perform some computation on top of that stream. You output the data. So this is how you can do streaming with with Spark streaming library with the new structured streaming API. So you might have a stream come in, do some ETL, performs interact with machine learning libraries. You might want to write something to disk, generate reports, ad hoc queries. These are all things you want to do on the same data set at the same point of time. So structured continuous applications or structured streaming API would facilitate in developing this kind of applications that react to real-time data. So these are all the yeah. Can you go back? So these are all the different moving parts that we discussed. You want to perform ad hoc queries. You want to output the data. You want to run. You want to generate some reports out of this data at real time. So these are all the moving parts that you have to that can be possible. That can be possible, or that can be handled with continuous applications. So this is how this is the primary difference between structured streaming and continuous applications. Structured streaming by default uses micro batch execution model. This means that the Spark streaming engine periodically checks the streaming source and runs batch queries on new data that has arrived since the last batch ended. In this architecture, the driver checkpoints the progress by saving the record's offset to a write-ahead log, which may be then used to restart the query. Note that so with structured streaming, uh, what happens is we have the similar concept of micro batches. So you provide a trigger and you define a specific time. Based on that time you provide, what it does is it does micro batching, and the data that accumulates in that specific time interval will be executed. That is about the structured streaming. When comes to
So one of the point which you need to remember with respect to structured streaming is you are introducing a bit of latency in the process. So you have to tell whether you want to process every 30 seconds or 1 minute or 2 minutes, whatever it is. That is additional latency which you are adding on top of the data since it is generated on the source. So with continuous applications, it solves the problem. The processing engine, the streaming processing engine itself will not introduce any latency to the process. Even if there is latency, it will be very minimal.
Yeah, with structured streaming, right? Whenever a data is available, what Spark driver would do is it will do micro batching based on the time interval you provided, and it will distribute this processing to multiple executors, right? This is how Spark streaming would work, but with structured streaming, you have a flexibility to provide that latency. You can control that latency. So with the continuous mode, it is slightly different. Instead of launching periodic tasks, so here what you do is periodic task. When the data is available, it will create few tasks and it will assign these tasks to the executors, and executors would process it. With continuous mode, it is a little bit different. Instead of launching periodic tasks, Spark launches a set of long running tasks that gets continuously executed on the executors. So driver is responsible for that. Once you define this configuration, this is a very small configuration change. Once you do this configuration change, what your Spark driver would do is it would start long running tasks that continuously wait for data. They process the data and they flush the data out. They write the data back to disk, back to any Kafka topic or any RDBMS. The driver says, here is the data, go and read it. Since events are processed and written to sync as soon as they are available in the source, we can get end-to-end latency in few milliseconds. That's the main difference. So with structured streaming, you still follow the same concept of mini batching. With continuous applications, there is no concept of mini batching. So continuously running tasks are initiated on executors by Spark driver, and these running jobs will accept the data. Whenever the data is available, they get computed, and the results will be given out. All these what do you call, uh, all the offset management and everything will be done by Spark driver, and they use write ahead logs to log all the uh, what do you call, all the commits that you're performing on top of the continuous application. So this is the demo use case. This is the a demo use case that I want to illustrate in the today's demo. Here is a simple structured streaming ETL pipeline. So logs. This is not a real-time project. This is a simple use case that we came up with just to demo and to understand what is this continuous application is, how you can configure this continuous application. So logs are generated.
Oh, I'm sorry. So now it should be clear. Can you hear me? Hello, can you guys hear me? Yeah. Can you guys hear me? Okay, now it is fine. Okay, cool. So let me reiterate what I'm talking about. So here we have created a demo on a hypothetical scenario because he cannot share the details with respect to his project and code directly, and hence leveraging his experience, we built a scenario using a simulated web application being logging information into the log file, and we built the demo on top of it. He is using a similar approach to analyze the log files as part of his current project. However, we cannot get into too many details with respect to that. But this can be applicable to any streaming use case in many of the organizations. Most of the organizations are actually implementing solutions like this using different technologies. For example, LinkedIn solves similar problem using Kafka with whatever streams. Sorry, along with Kafka, there is something called Kafka streams. Most probably, LinkedIn might be using Kafka streams to solve this problem. Whereas here, as they are getting data from AWS files, they have decided to go with continuous applications using Spark streaming. That being said, now he will get into the details with respect to the demo. First, he will give the high level overview, and then he will actually get into the hands on.
So logs or events are generated by web apps, mobile device, or point of sale systems. These logs, we are delivering these logs to an intermediate S3 bucket using Amazon Kinesis. Amazon Kinesis is a fully managed service for delivering real-time streaming data to destinations such as S3, Redshift, Splunk. So we are using Kinesis Firehose to deliver these application logs into an intermediate bucket. These logs are basically text files. These logs are generated by Genlogs application. This intermediate data will be used by multiple downstream systems. One of the downstream system is our Spark structured streaming application. Here we are using structured streaming file sync API. The source is an S3 path. What we do is we listen to this intermediate S3 bucket. Every time when a file gets generated, we process this data. We perform computations on top of this data, and we are syncing back to an S3 bucket. We have built a Hive table on top of this S3 bucket. We also do partitions in the Spark streaming application so that the real-time data gets reflected when you query on top of the Hive table. Let's go and do a quick demo.
So meanwhile, before we get into the demo, if anyone of you are new to Spark and if you want to learn Spark, you can shoot an email to us, training@itversity.com. We provide vast array of courses in the space of data engineering. There are a lot of courses on Spark and Kafka using programming languages like Scala, Python, etc. So whatever is relevant, we try to be up to date, and you can sign up for any of these courses. That being said, if you like the content so far, please click on the like button here. It means a lot for us. You can also share with your friends who is interested in exploring these big data technologies by clicking on this and sharing on other social networking platforms. It means a lot for us, and thank you for doing so in advance. That being said, again, I am reiterating, if you need any information with respect to the trainings we provide, they are available at you can shoot an email to training@itversity.com. So our folks will actually give the email ID in the chat, and then you can take it from there. That being said, I'm handing it over to Sarath again, and he will be taking care of the demo. So the reference material and code, everything is available as part of this blog. So you can actually sign up to our platform and access this material for free. The link is also available as part of the description. That being said, let's get into the demo.
All right, let me copy paste it. Where is
So in his project, he is using AWS EMR. However, we did not spin up a AWS EMR cluster to demonstrate this. We can leverage our existing big data labs for most of these, most part of the demo. But in his actual project, he is working on AWS EMR. Between AWS EMR and open source Hadoop or any distribution, Hadoop and Spark, there won't be any difference. However, if there are differences in the versions, some things might work in AWS EMR and it might not work in other clusters. So as long as versions are compatible, the steps are same.
So we are importing functions from PySpark SQL library. And let me start by going through the code. First, what you do is you define a source. So this source can be a Kafka topic. Right now, we are using, as part of our demo, we are using FileSync API. So we are listening to the intermediate S3 bucket. We are not actually taking care about, we are not actually looking about how the data is being produced. What we are defining here is how we can process the data that is being produced from weblogs. And this data will be delivered to S3 bucket using Kinesis Firehose.
Let me show where our S3 data is by going into AWS S3 bucket. So I'm connecting to my AWS account. So once we are in the AWS account, we can actually go to the AWS console. Let me get into the AWS console actually. So here I'm getting into my S3 bucket where the data is being generated. So we have a Kinesis Firehose as well as Kinesis stream running behind, which is populating the data into this directory structure. So ITversity data is the S3 bucket name, and 2018 is the directory name which is created based on the year in which we are getting the data, and then month and then R. So every R there will be a sorry, it's date, and every date there will be an R, and for every R you will see files here. Typically the file size will be pretty big, but as we are just using some simulator, the file sizes are small here. Okay, so this is how means using Kinesis we are getting data here. We are planning to come up with a holistic course with respect to AWS analytics, and as part of that we'll be covering how to configure Kinesis stream and get data here. Me and Sarath will be working on a course to cover each and every aspect of AWS analytics services category. That being said, from here he is going to read the data using FileSync API, and he will walk you through, and I'll be typing the code. Can hear me and also watch the screen. Can you guys confirm? Hello? Can you guys see the screen? So let's give some more time so that people actually join. Okay, just give me a moment. Some things got messed up here. It got restarted somewhere, so I'm opening it up and fixing that issue. Yeah. Now it should be fine. So he will be walking you through the demo, and I'll be typing the code. Okay.
Okay. So first you have to provide the source from which you want to actually read the data from. This source can be a Kafka stream. It can be a what do you call, a specific directory. When you read it from a specific directory or a file system, we call it as FileSync API. When you read it from a Kafka stream or Kafka topic, right, you can also configure the format as Kafka. You can provide the topic name and the details. Here is the piece of code to read the data from a specific S3 bucket. So this data is getting populated here by application logs, and these logs are delivered using Kinesis stream. That's the upstream system. So here we are reading the data from that S3 bucket. We are initiating a stream. Instead of reading the data, this is not a static data. The data gets updated in this directory. So that's the reason we have a star. So we listen to any of the new file that is coming into this specific file directory. Once a new file arrives, your read stream will pick that data, right? And that data will be available in streaming data frame. Now, let's see the schema of this data. Yeah, so this is the schema. This is like a JSON string, so that has many details, many log details. The next thing what you can do is you can perform many transformations, and you can also use high-level Spark Core APIs, or you can perform a few kind of actions on top of this data frame, the way you do on the static data. All right. So now I want to get department details.
We will be getting the department count from the input data. So let me walk you through the how the data look like. So I'm connecting to another session here. So here I have opened another session, and I'm connecting to the lab. And let me run a command called tail underscore logs.sh. It will actually give us a preview of the data that is coming into those S3 files. And you can see the message. So this message is kind of a log4j standard message which is being written by a web application to track the visitor traffic. So someone have asked earlier how to track these things. So we need to use APIs to write into a log file or into Kafka topic or whatever streaming technology you want to use in the middle, and you should be able to log the clickstream traffic to downstream applications. That being said, now we are trying to load this data into multiple files at each hour level, and as per our Kinesis stream configurations, we are trying to write into a file whether every 2 minutes or every 3 MB. So whenever the data size reaches 3 MB or whenever the threshold reach 2 minutes, you will see a file in S3 bucket. Okay. So that being said, from this data, Sarath is trying to process using a continuous application framework of Spark structured streaming and want to demo. So if you look at this here, we have given year, month, and date, and then we have given star. So we are actually reading all the subdirectories from this location at our level, and we are trying to process. So here we need to come up with two functions where we can actually extract the date information so that we can create partitions into the Hive table and store data at a bit different granular level, and then we'll take it from there. So the target table in Hive will have two level partition. One is at year, one is at date, and the second one is at year. At hour. So instead of having these many level of directories, there will be a date at a higher level, and then hour at a second level, and then we will be loading all these files to there. So that being said, we need to use this information, and we have to create those partitions as part of the Hive table. Here we are not going to demo using Spark SQL APIs how to create those partitions. However, we'll be pre-creating the partitions and we'll be loading data into those partitions. 1 minute. So Subramaniam is saying screen is not in sync. I don't know. We are still on the same screen. I did not change the screen. Is it for everyone or is it only from Subramaniam? Are you guys okay with what is going on, or do you see any discrepancy between sound and? Okay, is it fine or is it not fine, Pawan? Can you confirm? Okay, it is fine. Thank you. So that being said, again, Sharath will be explaining, and I'll be going to the steps. So just follow this, and I'll be typing.
We want to create partitions based on the file that you're reading. So we are reading files that are getting populated by date and hour. So we want to create a similar partitions on top of it. So we have defined two different what do you call UDFs to do that. These are very, very simple UDFs. We get the absolute path of the file that is being read using read stream. Absolute path, not the star directory. We'll get the absolute path of each hour, right? The file that we are reading. And what we do is we extract date and hour from this absolute path. So these two get date and get hour UDFs would extract date and hour from the absolute path of the file that is being read by read stream.
So we have created those two functions. Now let us validate before going further. Okay. So I'm creating a variable with a similar value as the path we have passed. So I'm copying till here. Okay. And then let me create a variable called dt and then paste it. I have to put it in either single quote or double quote. Okay, now dt is a string. And if you look at the code, we are first splitting by forward slash. So if I say dt dot split by forward slash, you can see, okay, sorry, it is dt. You can see the array. The array have string, then a blank string, IT data, year, month, date, and hour. So using this information, we have to build the date. So this function is taking care of that. So now if I say get date of dt, it actually use the split using forward slash, and it is extracting the information from fourth field in the array till sixth field. Fourth field is year, and the sixth field is um, uh, date. In between we have month also. So it is extracting year, date, and month, and it will actually create a two elements. And then we can join using join function, and this is the string which will be used to join. So that's why when I say get data of dt, it is generating a date using this information. Same is the case with hour. We want to extract whatever information that comes as part of this file. So here we don't have the actual hour value. So this will not work. But when we develop this, we will be passing each and every file name to this function. And then that function will be able to pick the hour. So let me simulate it here. I am changing this date dt a bit. And instead of star, I am actually placing an R and then some test file name. So this is how file names will look like. And then if I say get R of dt, it will actually get the hour part of it. So we are trying to extract this so that we can dynamically generate partitions in the Hive tables. And then as part of his original process, he is trying to create partitions in Hive table using spark.sql command and submitting alter command, and it is taking care of creating those partitions. However, we are not going to do that. We'll be pre-creating the partitions and we will be loading the data into those partitions. And hence we'll go further and focus on processing the data within the data frame, which is named as streaming data frame. Okay, so this is the data frame name. So we'll try to apply certain data frame operations on top of it to process the data further.
Okay, so next we want to register these UDFs. We have created two UDFs. We now want to register the UDFs. These two lines of code is to register a UDF.
Unless you register the regular Python function as UDF, you will not be able to use it as part of this Spark SQL APIs. As we want to use this as part of the standard Spark SQL APIs, we need to register like this. Once you register this, you should be able to use these functions as part of your Spark streaming data processing using structured streaming APIs or data frame APIs.
The next thing what we want to do is we want to get department data. We want to extract department data from the entire log that we have seen before. So that's the transformation that we are performing on top of the stream.
Yeah. So the problem statement here is we are trying to get the count for each department at regular intervals. And to get the department name, we need to look for those records which have department in them. Okay. So if you look into this record structure, you have the IP address at the beginning. So this is the IP address from which the traffic is coming, and then date, and then REST endpoint. And as part of this REST endpoint, it will tell which page is being navigated. And we are only interested in those pages which have department in that. So first we need to filter for those records which have a department in them like this. And then we have to extract this, which is nothing but department name. Using this, we should be able to compute number of departments at regular intervals. So let's come up with the logic to perform that. So here, let's start with print schema once again. So if I print schema on streaming data frame, there is only one record in one column in this data frame, which is nothing but value. And on top of this value, we want to add new column by name file path, and also we want to add the department name at a later point in time. Yeah, first let us filter for the lines which have department in them. So the logic will look like this. streaming data frame. This is the data frame name. And then so here we are recreating data frame with the same name after processing. So this data frame will have the entire data, whereas once the assignment operation is done, the new data frame will have only filtered records. It will not have everything. Here we will not be able to validate at each step because of the streaming nature of the application. If it is regular Spark SQL or data frames, we should be able to preview the output after each and every step. So if you subscribe to any of our courses, you will understand these things a lot more in detail. So that being said, I will not be able to preview at each and every step, but I will try to explain as much as I can. So now using this data frame, I can apply filter. Filter is one of the APIs to apply filtering on the data and get whatever data we want instead of getting everything. So here there is an API called split. So if you look at the record, to get this and compare whether it is a department record or not, first we need to use the space as delimiter, and then we this. Okay, so let's show me. Let me show you. Okay, so I'm copying this entire string.
This is one single log.
Yeah. So let me say log message, and then let me put it in single quotes and paste that log message. So it is nothing but a string. You can actually say type of log message, and it will give us the data type. Once you have a string, you can apply split using space as delimiter, and you can extract this by reading that particular element. So let me show you. So here I am saying log message dot split of space and hit enter. You can see it has created a list. Lists are represented in square brackets in Python. That's why you see square brackets at the beginning and the end. If I want to read the first element, I have to say of 0, and it will give the first element. However, I want to read this part so that I can compare whether it have department or not. So to read this part, I have to count the number. So this is 0, 1, 2, 3, this is 4, this is 5, and this is 6. So if I say 6, it will actually give us the endpoint which have the department name and categories. From this again, I have to extract this and compare if it is department or not, so that we only consider those records which have department in them. Others should be ignored. For that purpose, we have to use split once again. So this is Python split. And in this case, the split character is /, and again it will return an array. So to read the second element, I just have to say of 1, and it will give the department. Then I can actually compare that with department. And if it is equal, it returns true, otherwise it returns false. So when we use apply, when we use filter and apply this logic, it will only consider those records where this portion is department, otherwise it will ignore. Okay, so when it comes to data frame operations, the APIs is a bit different. It is similar to SQL type syntax, not programming language syntax, and hence we will be using the function like this: split off the attribute name, and then you have to give the delimiter, so on and so forth. So let me copy paste the code which is already there for to save some time here. I'm going to this, and I'm actually copy pasting this one. Okay, so now you see we are actually applying the filter, and as part of the filter we are applying split twice, and we are actually reading the column value from streaming data frame. When we say print schema, it has one field which is nothing but value, and we are reading the elements from that column, and then we are splitting using space first and then /, and then we are reading sixth element after splitting with space, and second element after splitting with /. So this is seventh element, not sixth element, and then we are comparing with the department. And also we are using a API called with column, and we are creating a very additional column in the data frame called file path. There is a function called input file name. and using that input file name, we can actually get whatever file name is passed to the program. So we have bunch of programs within the directory, but we are passing all the files with using star, right? So here, when the program is running, we should be able to access the actual file name. And the way you can access is by using this function called input file name. So we are trying to get the input file name and casting it as string, and we are adding it as additional column to the streaming data frame. Earlier streaming data frame have only one column, which is value. Now if you actually say print schema on streaming data frame, it will have two columns. One is value and the second one is file path. And this file path will have a file name for each and every record. So if a file have 100 records, all those 100 records will have exactly the same file name in the second column. Okay, now we should be able to apply additional logic. So we want to perform the department count. So to perform the department count, from this we have to extract this information. So from the value which have the which have this which have only the those records which have department based endpoints, we need to extract the department name, which is this one, and then we have to perform the word count. So now let me show you the logic for that. Again, we are using split. So you can see the split here. First, we are splitting by space, and we'll be getting that endpoint. And after that, we are actually splitting again with forward slash, and we are getting the third element. So if you go back to the logic I have shown here, earlier I am using off1, and off1 is giving this part. When I say off2, it will give this part. So using that information, we should be able to compute the department count. So for that reason, as part of this logic, again, I'm copy pasting this one, and I will be explaining. So we are creating a new field name called department name, and the department name will only have this part for all those records where there is a department based endpoint. Apart from this department name, we are also adding two more fields, date and hour, so that we actually can copy data into the appropriate directories into the Hive table. And Hive table also need to have these fields because it's a denormalized table, and we need to have date field and hour field in the Hive table. And hence we are adding these two additional columns to the existing data frame. So using with column, you can add as many fields as you want to the data frame. And then to get the date, we are using the UDF, which we have registered earlier, and we are passing the file path, which is generated earlier, which will give us the file name. And from that file path, we are actually getting the date and also hour. Okay. Now, if you actually look at the print schema, it will have 5 fields. One is value, which is our original record, our original log message. And the second one is file path, which is extracted using input file name. And third one is department name, which is extracted using this with column, and then the logic after splitting each and every record by space first, and then by forward slash, and then extract the department name, and then the date, which is retrieved by the UDF, and then R, which is again retrieved by the UDF. Now, using this information, we should be able to load into the Hive table. However, we don't need to store file path into the Hive table. For that purpose, we'll be dropping that from the data frame. It's pretty straightforward. You just have to say streaming data frame. So earlier file path is required to get the hour and date for us. Once we get hour and date for us for each and every record, we can drop this file path. There is no value of adding it to the actual data in Hive, which is used to analyze. So we are using drop function. I need to assign it to a data frame. I will do that in a moment. And then you can actually say file path. Okay. And now this will have only 4 fields. Let us review whether we need to actually, we need to reassign to a different data frame. Okay. So here I have to say streaming data frame. So whenever we run these commands, it will always create a new data frame. However, we are using the same name here, and hence you will feel that we are updating the same data frame, but that is not the case. Now you can see that we have only 4 fields. Okay. Now it is time for us to process the data in streaming fashion. And actually, Sarath is using continuous, but due to some challenges with respect to the environment we have here. So continuous streaming works better with Spark 2.4, which is released recently. Our lab have only 2.3, and hence we will not be showing directly the continuous API, the continuous one. We will be using the micro batches only, but we will explain how to achieve the continuous also with the latest version of Spark. That being said, as we have used file sync API to read, same is the case with write. We are trying to write the data back to, let me show you here. We are trying to write the data back to S3. So we have to use a file sync API itself. And we'll be using Parquet file format here. And automatically Parquet files will be compressed with Snappy. And we'll see whether the data is being written to S3 bucket or not. And also we'll be creating a Hive table on top of it to preview the output. That being said, it will look like this. Data stream writer. This is a new variable we are creating. This is not. This will not be of type DataFrame. This will be of type some stream writer. And then on streaming data frame, we are using an API called WriteStream. It is similar to read. So in terms of read, we have used readstream. For writing, we have to use the WriteStream. And then you can specify the format. You can say console to print onto the screen, or you can say the file format to write into the file system. So here, first I will show you on the console. Okay. Once you specify format as console, we can actually specify the output mode. So there are 3 output modes. Again, we will not be able to cover what are those at this time. You have to. Okay. Actually, Sarath will talk about output modes in a moment. First, let me show you the demo, and then I will hand it over to Sarath, where he will be explaining about the output modes. That being said, here the format is console, and the output mode we are using here is nothing but append. Once you specify the append mode, then you just have to specify the trigger. So this is where a micro batch based streaming application and continuous application will differ a bit syntactically. If it is continuous, you just have to say continuous, and then equal to, you just have to specify at what interval it should checkpoint. In this case, it will not try to read the data every 1 second or so. Whenever data comes in, it will just process. Even if you specify 10 minutes, it will not wait for 10 minutes if we say continuous. It will just read the data in continuous fashion, but the checkpointing will happen every 10 minutes. Okay, so that is the difference between regular structured streaming or Spark streaming and continuous processing or continuous applications. So if I say continuous 1 second, every 1 second it will checkpoint, but it will keep on processing the data as and when data arrives. So this is how you can actually. Okay, there is a typo in my data frame name, so let me fix it. Okay, so even though it written, it doesn't mean that it is running. So because of the lazy evaluation nature of our data frames APIs, only when certain actions are performed, the execution start. The action which needs to be performed to start the execution is nothing but data stream writer start. If you are trying to write to the file system, you have to specify the path so that the data is written to that file system. However, we are just printing on the console, so we can just say start here. See here, it is failing because of the incompatibility with respect to Spark versions where Sarath was working and where we are trying to demonstrate. But if it works, it will just keep on reading data whenever data comes, but only checkpoint based upon the value which we have passed as part of continuous equal to. Now let us replace this with processing time so that we actually see some data in action. Okay, so here I just have to change. Sorry, this is not correct. I have to use the output mode. Or even if we do not specify output mode, it will try to use the default one. Here I am saying processing time equal to 15 seconds. If you say processing time like this, it will actually queue up the data up to that point, and then only it will process. It will not process the data as it arrives. So here it is actually adding the latency. So this is the primary difference between regular streaming and continuous applications. With respect to continuous application, the streaming layer will not add any latency, whereas with typical standard processing or legacy processing, it actually adds some latency. In this case, it's up to 15 seconds. And now hit enter, and then you can actually start, and you will see the data coming on the screen. Now see, it is actually using 200 threads to process the data, and you will see the output in a moment. It will take some time because as we are running for the first time, it has to process a lot of data, but from the next time, it will be a bit faster. Every 15 seconds, you will see the data immediately on the screen. So this is the first set of data which we got. You can see here, the trigger interval is 15 seconds, but spent 22 seconds to process, and hence it is falling behind. It is just a warning to you. However, because there is a lot of data queued up, it took some time. After first batch, as we are not getting a lot of data, it will be done within the 15 seconds, and you will not be getting this warning. So sometimes your processing might have stopped for a few hours, and to catch up, it might take some time, and during that time you might see these kind of warnings. As long as the falling back is going down, you are good to go. If it is falling behind, means the falling behind is being increased at every interval, then you have to by dealing with it. You have to fix where the issue is, and you have to take care of it. So let's wait for a few seconds and see whether we'll be seeing the next batch.
New data will only be updated for every minute. That's how Firehose is configured.
Yeah.
So we have to wait for, I think, 2 minutes.
Yeah, we have to wait.
So there is no data at this point. So the new batch data is not available right now. The data is available. So we processed the data. We
saw the first batch, and then it took some time to see the second batch. So now we'll be seeing every minute or two based upon our Kinesis configuration. Only when new files are added to S3, it will read the data. Otherwise, it will not. Okay. Now let us see how to write into the files. So we just used code to print on the screen. For this, we need to kill. And unfortunately, with respect to streaming applications, we cannot just start writing in the same session. We have to come out of this completely, and we have to restart the PySpark. I'm just changing port because if it is not killed yet, I don't want my session to fail. That's why I changed the port. Our cluster have multi-tenants. A lot of active users are there, and then it will not fail if we actually give unique port if you are also the user in our active cluster. That being said, as we have demonstrated most of the code, I am just copy pasting from here where we have the import statements till this path, this part. Okay, so now instead of using a format console, we'll be using format parkway. And also we are trying to checkpoint into a S3 bucket so that we'll be able to recover without any issues if it stops in between. If we don't have this, then it will try to manage itself, and sometimes we might lose that information. It is better to store persistently, and Sarath will talk in a moment. Let me finish the demonstration and I will hand it over to Sarath. So that being said, again, here we are using processing time rather than continuous, just because we are running into issues. We will actually come up with working code with appropriate environment, and we will actually share if there is any difference with whatever we have here. That being said, let me copy paste this as well. So you can see here, unlike with console, when we actually use start, we have specified the path. So it will actually try to write to that location. If you fail to specify the path, path, then you will not be able to see the data. And sometimes the session might be running continuously but not writing to anyone. So it is important to specify the output path here. This is checkpoint path. This is the actual output data path, and hit enter. So now it will start processing the data and it will be writing to the file system. So while it is running, Sharath will cover some of the concepts. Let me go to the PowerPoint here, and then we'll take it from there.
So I'll walk through the code. In the next slide, we have the important pieces of code, not the entire code. So how do you configure? So to build any structured streaming application or continuous application, right? So you have to configure three things, and we also have other configurations. Let's go through each of the things that we do. It has three stages of these steps that you have to do. The first step, you have to provide the sink. This sink can be a Kafka topic. This sink can be a file, what do you call a file system. Right now here we are using S3 bucket. You can also listen from a HDFS path. If you're running this job on an EMR cluster, beneath it you will have HDFS. If the data is getting populated onto HDFS, you can use that as your source. You can configure multiple sources. These are all provided as part of this structured streaming. Next thing, what I'm doing is I'm performing all type of transformations. Right. First, we have done a filter operation on the data frame. Likewise, we have done with column. We have added new columns to it. So these are all a simple transformation. You can also do complex transformation. So we are just adding columns to the data frame. We are performing a filter operation. We are using UDFs, user-defined functions, to get the date and hour of the file that you are reading, to partition the data so that the results can be reflected onto the Hive tables. That's the only purpose why we have done why we have added date and hour, and this is about the transformations. You can do complex complex API transformations. We have, as part of the demo, we have done simple simple transformations. And the third part is next you provide the output format, right? Next you provide output mode. So the output mode we totally have three output modes you can configure. The first mode is complete. If you want to do some kind of debugging, you would probably choose to go with the complete mode. So when you configure it complete mode, suppose like on 30th day in the first hour, you have 10 files, right? 10 files already generated, and now you are trying to process the 11th file. So when you configure the output mode as complete, every time what it does is it will fetch all the 10 files that it processed. So what it does is it will read every file from that S3 path. Every time a new file comes in, it'll read the entire data. So basically what you do is you work with complete mode when you want to debug the entire workload, right? Then you go and configure the complete mode. The aggregations or the transformations that you perform on this streaming data frame, right, you will be doing on the complete data that has been handled by readstream up till that time. So mostly we use append or update mode. The difference between append and update mode is append will only process the new rows that have come in the stream. It will only process the 11th file. 11th file. It doesn't really care about the rest of the 10 files because it already processed these 10 files. It has done computations. Here it moved it to a different S3 path. So it doesn't really care about all the other 10 files that it processed. It will only look for the new file that is being read by read stream. And update, right? Update is, it'll only care about the new records that got updated. So it will read the entire data source, right? It'll do an operation on top of it, a filter kind of operation on top of it. It'll identify what are all the rows that got updated, and it'll update. So this is the main difference between append mode and update mode. So the next thing is you can provide trigger. So this is where you classify or you differentiate structured streaming versus continuous applications. If you configure processing time in the trigger, then it is a structured streaming application. If you configure continuous and provide a time interval, then it is a continuous application. That's only the difference. So initially we discussed that how the tasks are assigned, right? Once you configure our processing time, right? Once you configure processing time, the Spark driver would wait for the new data. Once the new data is arrived, what it does is it'll get the data based on the time interval. It'll create mini batches, and it'll distribute this processing to multiple executors. That's how a structured streaming API is done. Structured streaming API processes the data. So it will create mini batches based on the seconds that you provide. And when you configure continuous, right, no matter, right, no matter data is available or not, it will initialize tasks, right? It will initialize tasks on the executors, long running tasks, right? They keep on running. Once the data is available, the driver would recognize this data. Then the driver would say, hey, executors, you have a running process available. Do this transformation, do this computations on top of this data, flush it out to S3. So there is no latency here. So to get the best performance, right, to get the best performance, or the use cases where you want the highest latency, the lowest latency, right? The lowest latency, then you go and configure it as continuous applications. This configuration is completely based on the use case you're dealing with. This is not available, or this is not applicable to every streaming use case, right? If you want the lowest level of latency, you configure or continuous. There, when you are working with AWS, there are certain caveats to work when you're working with continuous applications. I think we have a questionnaire session, and I'll try to dig deep into the caveats that we have working with S3 file system when you have configured continuous application.
So now let us create the Hive table on top of the data which is being written to S3 bucket here, and let us run queries also using Hive. So again, there are certain limitations because we are performing demo on our cluster. We will not be able to read data directly from S3 because of the settings. Means we can, but it is a bit complicated. To simplify it, we are actually copying data from S3 bucket into HDFS on our cluster, and we are creating an external table and then running queries on top of it. In actual projects, we don't need to do that. If you are building the solution with AWS EMR along with Kinesis and Spark streaming, you don't need to copy data from S3 into HDFS. You can directly run queries on top of S3 by creating external Hive table. That being said, this is the directory which we need to create in HDFS. So we have created the directory here, user training streaming. In that, we are actually copying the data from S3 bucket. Yeah, so let us go through this S3 bucket and see what we have there. So earlier, the input data is coming from this. 1 minute. I think my streaming, yeah, now it is fine. I thought YouTube streaming is stopped and you are not able to see the screen. So now you see here, this is the input data. And if we actually go back to the ITversity data and go to the output path, which is specified as part of our logic, where is our logic? So it is here. You can see here, this is the output directory, ITversity data output. So if we go there, you should be able to see the output files. This is for date 2018 November 28th, and you can see a directory for each hour. and you can get in there, and you should be able to see the files in Parquet format with snappy compression. We will not be able to preview the data directly here because these are not regular text files. However, we can create a Hive table, and we should be able to query the data from these files. So that being said, here I'm launching Hive. Once the Hive is launched, we need to create the database. Oh, sorry. First, I need to copy the data. Without copying the data, it will not work. So let me exit from here and let me copy the data. So I'm copying from S3 to HDFS location, which you have created earlier, which is nothing but user training streaming output. And you see all these files which are generated by our streaming job is being written to HDFS location. However, when it comes to the actual project, we don't need to do this step. So once the copying is done, then we can launch Hive, and we can actually create the database by name streaming. Yeah, let us finish the demo, then you can highlight. So he need to talk about the checkpointing, which is very important concept, and then we will actually get into the questionnaire after completing the demo. So still it is 16th hour, so it has few more files here. Once it is done, we will actually get into the rest of the demo. So it will take another 20 minutes to half an hour because we have questionnaire, and also there are plenty of good questions which we want to respond. If you are watching this session after streaming is done, then you can actually access our blog post, and under the blog post there is discuss.itversity.com link. You can click on that, and you should be able to ask questions here. Me and Sarath will monitor this, and we'll actually respond to your answer to your questions, as long as they are relevant for the current topic. So probably 30 seconds more, then we should be able to proceed further and complete the demo part. Okay, still there are so many. So it will take another 30 seconds or so, because first I think it have copied files from 0, 1, and then 10 to 20, and then 2, and then 21 and 22. Now it is actually taking care of 3, 4, 5, 6, 7, 8, and 9. So just another 10-15 seconds. We are almost done. Yeah. Now let us launch Hive, and then go back to this code. Let us create the database streaming. Use streaming. Again, if you want to learn more about Hive and all, we have courses. You can reach out to us at training@itversity.com or support@itversity.com, and we will be able to take care. Okay. And then we have to create this sectional table pointing to the new directory which is created. First, let us validate whether that location have files or not, just to make sure that there will be no issues. So first, I am actually running Hadoop fs command to see what we have. Oh, there is a subdirectory under output, so which is not correct. So this will cause some issues. So again, I have to come out of this. So let me kill this, and then let me. Yeah, that's correct. So what we'll be doing is, instead of only giving up to output, we'll be giving the subdirectory which is generated. So which is nothing but output and output. Okay. So here I'm only copying till this point, and then giving output, and then hit enter. Now the external table is created, and then we should be able to preview the data by saying select star from event logs. Yeah. So there is one more thing which we need to take care. We have to create partitions like this so that we can actually access the data. So here also we need to make some changes. So as part of his application, they are taking care of it programmatically. Even before processing the data, he is using spark.sql, and then using alter table command, he's creating the partition by using the date and r he retrieved from the file path. However, instead of showing that as part of the demo, here we are manually creating the partitions. So here we have data for 28th November, and hence we have to specify date as 28th, and then our 12 is there, so we are creating only one partition. Okay, once that is done, I have to specify the location also. Sorry for that. I will be creating another partition with different hours, and then location. Yeah. So location also we need to make the modifications, and also we have to specify output here. 1128 slash HR equal to 2, and then a new partition will be created. Then we can actually say select star from streaming.event logs limit 10, and you should be able to see the data. So there are some issues because of the way we have done some of these steps. One of the okay, there is some temporary issues. This is fine. I don't think this is a showstopper. And also we did steps in a bit out of sync manner. That's why we might run into these issues. But if you actually do it the way it is documented, you should be good to go. Okay. So that being said, we will update, means we will troubleshoot further, and if there are any issues, we will actually update the documentation. So from here, once you have data in Hive or S3 bucket, you can actually deploy a reporting tool on top of it and run queries accordingly. So in some companies, they use Parkway, Presto, which is a Facebook solution which comes as part of the EMR to run ad hoc queries and generate reports. In some companies, they use Tableau, ClickView, etc. to connect to the S3 buckets and run reports from it. Okay, so this is the end-to-end demo, and there is one more concept which needs to be covered, which is nothing but checkpointing. Sharath will cover that very quickly, and then we'll actually get into the questionnaire between me and Sharath, and then we'll open up the public questionnaire.
Can we go back to the slide? So here we have covered the output modes. We have 3 output modes: complete, update, and append. And here you can configure checkpointing. Checkpointing will guarantee end-to-end exactly one semantics. This is where you configure it. So initially, right? When we developed Spark streaming applications, we used to take help of Zookeeper for maintaining the for doing the checkpointing. So here, right, Spark has provided the internal mechanism for checkpointings. So Spark will keep track of what you have read and what you have not read in that specific S3 location. Even though the application fails, right, your application, when you're performing a computation, right, for some kind of reason, if the application fails, you can again reinitiate a stream on the same location. It will go and look for the checkpoint directory. We are configuring the checkpoint directory S3 itversity / checkpointing. In that specific directory, open the directory. So we have internal directories created by Spark, and you're not taking you don't need to worry much about it. So all the commits, right, all the commits, offset management, right, everything will be taken care by the structured streaming internal architecture. You're not actually, you don't need to consider anything about it. So if you want to create a end-to-end exactly one deliverable streaming application, you configure the checkpointing. Even though there is a failure, you know, fix the application failure that you have You can rerun on the same S3 location. It'll identify what are the files it has read, what are the files it has to be, yeah, what are the files that are left to be read. So it will do all the checkpointing. So when you are streaming applications, and if the application fails, so you are accessing a Kafka topic, so for some reason, right, that Kafka topic is not available, and your downstream system, your Spark structured streaming application will fail. At that point of time, right, what you have to do is you have to just restart the application, fixing the Kafka issue that you have. So the driver would go and look into this checkpoint directory, right? It has the offset values, it has all the commits that it has done. So it will go and verify that, right? It will identify what are the messages that it has read, what are the messages that are still to be read, what is the, but the recovery would take more time, because if there are like 10,000 messages that are not read, it'll take certain time to recover from the failure. This is one of the thing that we have to consider when building a continuous application. So Spark driver would take care about the checkpointing. You don't need to understand what it internally does. You just configure that path. All the checkpointing will be handled by Spark itself.
So let us get into the questionnaire so that you understand what is being used in the actual project. So the first question is, can you give us an overview of infrastructure for building a streaming pipeline platform as part of your organization?
Okay. So I work for GrubHub. GrubHub is a food ordering platform. We'll have huge volumes of orders at the peak hours. The peak hours are lunch and dinner times. So we process thousands and thousands of order in that specific peak hours. So our applications, the web application, or IoT applications, or POS systems that we have, or the mobile applications, what they do is they generate events, and these events are handled by Clickstream, and uh, all these events produced by the Clickstream will be pushed into an S3 bucket using the Firehose, the same configuration kind of thing. We try to simulate the similar kind of demo. So the Clickstream would generate the event logs or events, and what we do is we push this event logs to an S3 bucket using Firehose. So then what we do is uh, uh, basically, the reason why we went with an approach to build uh, what do you call continuous applications are, we want to come up with a solution that has lowest latency possible, right? When there is a downtime of the application, uh,
So we'll discuss about those things a bit later. For now, just focus on the infrastructure,
okay.
like AWS and whatever technologies you are using. I think you are using AWS quite extensively, and then Kinesis to push the data into for the downstream applications, like LinkedIn using Kafka for the similar purpose. And then you are using bit of technologies, and one of them is streaming, Spark streaming to process that data. I think that is the answer for that question. Now let us talk about why you have chosen AWS EMR over on-premise cluster.
So we are completely, all the data platform is completely hosted on AWS. We don't really have on-premise clusters. So we have no on-premise clusters. Every data that we process is on AWS. So we leverage all these AWS what technologies like Kinesis, Kinesis streams, EMR clusters. EMR clusters to process the data. So and we yeah so all the data that we have is on Amazon, and we use all the Amazon services to process the data.
So how are you managing the life cycle of the cluster and business logic?
So the cluster management and everything we are handling with a scheduler called AskCommand Scheduler. We have built a proprietary API on top of this AskCommand. AskCommand facilitates to build what you call plugins custom plugins. We have developed custom plugins on top of this Escoban scheduler to spin up and spin down the clusters. This is the proprietary API that we internally built to manage the life cycle of streaming application or any ETL application.
So you use Azkaban to build the cluster, process the data, and terminate the cluster. Is that right?
Yeah. If we want to start a cluster, right, what we do is we will initially create an Azkaban project that has start cluster step, right, processing step, and stop cluster step, right. You configure in the start cluster step what is the type of cluster that you want to bring up, how much time your cluster has to be up, what are the number of nodes that your cluster has to have, that kind of thing. For streaming, right, we are having static clusters. These static clusters will be running 24 hours. So that's how we manage all the clusters. We manage everything with Azkaban.
So based upon my experience, a lot of startups and also quite big companies work on AWS. So AWS have this neat feature of pay-as-you-go model, and also they provide a lot of functionality around it. So they automated creating the clusters, terminating the clusters, and all those things by providing the APIs. You can also extend those APIs and do whatever you want. So wherever you have lower to medium range data processing capabilities at not so regular intervals, then leveraging those features can cut down the cost significantly. For that reason, most of the companies uses AWS EMR or the AWS analytics services in which EMR, Kinesis, and all are part of to cut down the cost significantly. That being said, why you have used the Spark streaming instead of Storm or Flink?
So we are using, as I said, we are using AWS for everything. So what we do is we create a EMR cluster. We do all the computations on that EMR. All these we run Spark applications on top of that EMR cluster. We stop it. So this is how we process the data. For streaming applications, we have static EMR clusters. So no, when you want to install these libraries like Storm, Flink, you have to install them as bootstrap actions, and you have to take care about it. The versioning, right? So right now, the latest EMR version is 5.1.9, 5.19, I guess, 5.9. This is packaged with Spark 2.3. So initially, we have so many batch processing ETL pipelines. So we wanted to migrate to Spark streaming. So we have Spark 2.3 packaged with the EMR 5.19. So then that's the whole reason. Bootstrapping, you have to take care about it. Any updates to Storm library or Flink, you have to take care about it. But when you initiate a EMR cluster, Spark is inbuilt, and with the EMR 5.19, Spark 2.3 and above is available. That's the only whole and sole purpose on working with Spark streaming. As I said earlier, Spark is a unified solution for batch processing, streaming, machine learning, graph building, working with many other libraries. So that's the whole purpose why we have inclined towards Spark streaming rather than other technologies.
So the next question is, what is the source and target of the datasets?
So here, so I want to give you one simple use case that we do. So what we do is this click, the events will be, we don't really care about the upstream systems. What we do is our event source is an S3 bucket. Our event destination is an S3 bucket. We massage the data in between it, and both the source and destinations are S3. We have Kafka as a source and S3 as a destination. We have Kafka as a source and Kafka as a destination again. So we have multiple use cases. Mostly we work with Kinesis, we work with Kafka as input stream, file sync as input stream. We have data in S3, we have data in HDFS. So we process this data, we push this data to S3. We again, after performing the computations, we push back to a different Kafka topic. So these are typically the source and target roles.
Okay, fair enough. So next question is, as per our discussion, he told that there are some challenges with respect to S3 for checkpointing and all, and they have overcome with EMRFS. So I just want to understand more about it so that people are aware of that there are some restrictions with respect to S3 being used as a checkpointing location, and how EMRFS can actually solve.
So here, right, when you are designing a continuous applications and you want lowest latency, basically when you go for continuous application is when you have huge data, when you're processing huge data at very lowest time interval, right? So Amazon S3 provides read after write consistency for puts. Amazon S3 provides eventual consistency to overwrite puts and deletes in all regions. This is where we have the issue. When you are processing huge data, right? When you are processing huge data, and sometimes some executors can fail when you're processing, when you're doing computations, right? So at that time, right, we are not able to guarantee exactly once delivery of these events. That's not an actual issue of streaming library. That's the issue of Amazon S3. The consistency of reads and writes is different. So, for example, if you have a big chunk of data distributed in thousands small partitions, and you're writing those 1,000 chunks to S3, after completion of writing, you start a read operation on the same data. At this point, S3 list operation may not show all the 100 chunks in the result. So you have put 100 small partitions into S3, and right away you're trying to read or you're trying to list out the number of files that you have in that directory. Even though you process the 100 chunks, you might get you don't really get the exact count. So even though the 100 chunks are present physically, the S3 list operation may take some time to give accurate information. So if you start processing at that moment, you are able to, so you will see some kind of data loss. So this is the behavior of S3. So in order to overcome this, right, EMR has provided a feature to enable consistency view. So they call it as EMR FS consistent view. When you spin up a cluster, when we are working with continuous applications, what we do is we spin up a cluster that has EMR FS enabled. Enabled so that all the read and write operations will be ingested into a DynamoDB. DynamoDB backed S3 buckets. We can call them as DynamoDB backed S3 buckets, where all the read and write operations are logged into the DynamoDB. So this is a very, very complex topic, it can't really be explained in a way. Go and look for EMR FS consistent view. That will give you a clear understanding. So when we are processing continuous applications, we can't really guarantee exactly one scenario when you are working with specific with S3. So that's the thing I want to.
Okay, so I misunderstood the discussion. So it is not that they are using S3 for the checkpoints or offsets. They are primarily using for the data. It seems with S3 because of the eventual consistency. It seems with S3 because of eventual consistency feature, the files might be put in the S3 bucket, and when we try to read, it might not give us the current status. To ensure that we are reading all those files which are already persisted into S3, we have to enable EMRFS because of the consistency view feature of EMRFS. The consistency view feature is facilitated by using DynamoDB along with S3 by Amazon EMR. That being said, the final question as part of our questionnaire is: what is your opinion on using Python for building Spark streaming applications? Please elaborate on any challenges or performance related issues which you have encountered?
So yeah, I started as a Java developer. Then I worked on Scala, and now completely in GrubHub. I'm working on Spark, on Python, completely on Python. So first of all, the learning curve of this is my experience. The learning curve of Scala was a little tough when I'm transitioning from Java to Scala, because the way you define functions and everything is a little different because it's a functional way of programming. So yeah, the learning curve for me, Python is very much easy compared to Scala. And when you are using Python with the Apache Spark or Apache Streaming, uh, I think Scala has better APIs or provides much more advanced functions. So I don't. Few things are missing in Python library of structured streaming. That's my overall observation, because you can't read. So if you, those are also available in the documents. A certain thing cannot be done when you're working with Parquet files. You can't really, what do you call, output that to a console. There are certain limitations compared to Scala and Python. And yeah, myself, I'm pretty much comfortable working with Python, because then the way you write your logic, or the way you express your iterations and kind of stuff is very less compared to, yeah, very, very straightforward compared to Scala.
So that being said, as I have been mentoring a lot of people, I think the reason why he feel Python so comfortable than Scala is, from Java he became a Scala developer, and from there he became Python developer. So all the pain of the transition from programming language like Java to more functional and uh, uh, whatever it is, programming language like Scala or Python, he already took that pain as part of transition from Java to Scala. Once you learn Scala, transitioning to Python is much smoother, because the programming paradigm, especially from the data engineering perspective, is almost same between Scala and Python. Anyway, that's my opinion. And that being said, there are few limitations with respect to Spark applications being running with respect to Python than Scala. Scala is faster. However, as we can scale up, if the performance is not up to the level we are looking for with respect to Python, and address that problem. So with Spark, we can mitigate that problem, but it comes at a bit of cost. That being said, as Spark is developed using Scala, most of the functionality they will be implementing with Scala, and it will be thoroughly tested. When it comes to Python, I observe that some of the features are not uh, uh, available with PySpark, which are available with Scala based Spark already. So those are few limitations. That being said, now let us actually get into the public Q&A. So there are questions already. So we'll take some questions and we will spend some time up to 15 minutes, and we'll try to answer as many questions as possible within those 15 minutes. Okay. So there are quite a few of them. If anyone is available, you can actually reiterate your questions now, so that we can focus on those questions which are asked now. And if we have time, then we will go back. So we'll start with Jayavardhan Reddy's question. What will happen if the source is not generating data for around 15 to 20 minutes? Will the streaming close the session, pause, or wait until it receives data again? So let me give it to Sharath, and he will answer that question.
So either way, you configure it as a structured streaming application or continuous application until you run stop. The way you started the stream, right? You can also give a command called stop until you stop the stream, right? Until you start the stream, it keeps on listening to that directory. So even though the data is not available, right, it'll always keep on listening to that. So if you provide processing time is equal to 1 minute and the data is not available for 15 minutes, for every 1 minute, right, it'll try to create a batch, and that batch would have no data, right? So next computations would not be performed because the data frame is null. So no other computations will be performed on top of it. That's about.
So the next question is Spark streaming structure. Okay, I think the question is Spark streaming versus structured streaming, which will give you better results. So I will answer that question. Spark streaming is legacy. Spark structured streaming is modern. From the performance perspective, I think both will perform almost the same way. But structured streaming will give you more developer-friendly APIs than Spark streaming because you can use DataFrame operations or Spark SQL to run queries on the structured streaming data, which is not possible with Spark streaming. You have to use underlying programming language APIs such as map, reduce, etc., which is a bit complicated compared to structured streaming. So with data frames, they try to unify the approach with all the modules and to make it a bit easier for the developers. And hence, structured streaming is better when it comes to development. From performance perspective, I think both perform almost the same. The next question is, if I don't use the trigger option, what are the differences between structured streaming and continuous streaming?
So if you don't really configure the trigger, it is basically a default structured streaming application. So if you are talking about the time interval, right? I think the time interval, I don't think we have a specific configured static time interval. I still have to look at it because I have never really configured without a trigger. So I know what the latency that I want from this data for a specific data site. So I didn't really try out completely eliminating the trigger.
I think there should be some default value and it will pick up that default value and it will process the data. Even if you do not specify trigger, internally it will use trigger. And by default, if you don't specify trigger, it is structured streaming, not continuous streaming. Typical structured streaming. So the next one is how to do deployment an on-premise with Spark submit command with arguments of number of executors and executor memory. So it is same as the way you are doing with regular jobs. Even in this case also, once we have demonstrated using REPL, but if we have to deploy it as application, we have to build a jar file or a Python bundle in the form of a zip file, and we have to schedule the Spark submit command. So it doesn't change. The next question is from Pawan. Is there any way to place streaming in sleeping mode? I doubt.
No, we don't have anything like that.
We don't have anything like that. So the next question is why Spark streaming, not Storm for streaming? You can use Storm or Flink also, but Spark streaming. Storm or Flink are dedicated streaming technologies. Beyond that, they don't have much of capabilities. Even though they might have, their bread and butter is primarily streaming data processing. Even Kafka have something called Kafka streams. It's not just Storm or Flink. However, Spark streaming have a lot of other capabilities. You can actually process data in batches using data frames or Spark SQL. You can implement machine learning algorithms as it provides unified approach to tackle different kinds of problems within an organization. Most of the companies where Spark is being used extensively go for Spark streaming over Storm or Flink. Then Chaitanya's question, to work on Spark, both Python and Scala are needed. No, one programming language is good enough to start with, but you should be able to adapt to whatever programming language the particular enterprise is using. Then only you should be able to, or you will be able to be relevant in the company. So, for example, Sarath started with Java, then he switched to Scala. He worked on Scala-based projects in Thomson Reuters. He did some POCs with respect to Python also while he was working there. Then he switched to another company. As that company is a Python shop, he adapted to Python. Now they might be exploring Scala for some of the projects, and he will be switching to that also if it is the case, so on and so forth. So you can start with one, and then you should be able to adapt to the other. But within a given project, no one uses both Scala as well as Python to build Spark applications. Either they will go with the Scala or Python to build the entire application. So Pawan is asking a use case. For my use case, every 6 hours I would get file. If I use the stream application, does it use resource background unnecessary? That is correct. You should not use streaming for this. It is a classic batch problem, and you have to come up with a solution using standard batch processing. And you can use tools like Azkaban to schedule batch, or even cron job if it is a POC. So there is no need to go with streaming. It will waste a lot of the resources on the cluster. So the next question is from Durga Prasad. When I use Spark action in Uzi, so we are not familiar with Uzi, so we are deferring this question. We don't want to give incorrect answer. At this time, we haven't used Uzi with Spark, and hence we are not taking this question. So Chaitanya is saying, I'm from DWH background, which is best for me. You mean Python versus Scala? Yeah, it's up to you. You can choose either of them. If you are completely naive, probably it's better to go with Scala, because as per my knowledge, most of the Spark-based applications are built with Scala, and considerable number is built with Python. So out of 100%, 10% might be Java, up to 50% might be Scala, and 30 to 40% might be Python. So this is the ratio. I will recommend to get started with Scala, and then probably learn Python also. If you know both, you will be able to work on 90% of the projects. If you only learn one or the other, then you will be able to work only on that 40% or 50% of the projects. So that being said, have a 6 month to 1 year plan and try to adapt to both Scala and Python over a period of time. Okay, so let us go back and see if there are any good questions, and then we will wrap up if there are not any more questions. Yeah, there is one question from Sai Kiran. Website clicks is one of the streaming process, right? So what will be the UI technology will be used to integrate for this, and how it is done? So clickstream have two aspects. One, the website itself from which data have to be streamed. Okay. So for example, we have this labs.itversity.com where we have our big data cluster deployed. Okay. So if I want to understand how many people are coming to my website, and if I want to run some analytics on top of it, I need to modify my source code to either log the clickstream data into a log file, or use Kafka APIs to directly log into Kafka topic or whatever technology I want to use. Once the data is pushed out of this in one form or the other into the intermediate integration layer, then we have to use technologies like Spark streaming and all, process the data, and pass that processed data into a NoSQL database or RDBMS database. And then from there, you can actually use any standard technology to report out of it. So this is the entire life cycle of streaming pipelines for clickstream data. It is not just from the UI perspective. You have to take care a lot of stuff. So one of the standard practice which most of the startups use is to integrate with Google Web Analytics. So Google will give a JavaScript code. If you actually integrate with your website, they will actually take the traffic data from you, and they will use that data, and they will actually provide you the report about your website. Using that, we can actually see what all pages are being visited by the customers. But if you want to build in-house, you have to pass the information one way or the other to the downstream applications, and then you have to process and get analytics out of it. Okay, so let me take one more question. This is the last one, and then we will wrap up. So it is from Durga Prasad. I am trying to pull daily transaction from SQL to Hive using Spark. Is it good to keep Hive partitions with date partition, or need to create year or month or day partitions? So let's defer this question. It is not relevant for today's topic. You can ask that question in our forum, and probably one or the other will respond to your question. So that being said, thank you very much for attending the session. Once again, please click on the like button if you like the content. If you want to share with your friends, just click on this and share with your friends so that we get some traction. And also, we'll be updating the blog with all the questions that are answered. And then we will take it from there. That being said, if you are new to IT University and if you want to learn any of these technologies, please send email to training@itversity.com. And one of our team members will actually help you. Also, we have a big data have an environment where you can practice. You can sign up at labs.itversity.com. So these are the plans for which you can sign up, and you can take it from there. That being said, once again, we thank you for joining the session, and we will catch up with you at a later point in time. Have a nice day. Bye.
Thank you, guys. Thank you for joining. If you have any questions, you can send it out to the discussion so that myself or some other guys from IT University can answer your questions. Thank you so much for your time.